Good afternoon, everyone. My name is Rhys Kelham. I'm an infrared application specialist for Perkin Elmer. If you're not aware of Perkin Elmer, we are an instrument manufacturer of quite a wide range of analytical techniques. So I've gone for this really snappy title of Maximising the Information on the Spatial Distribution of Tablet Ingredients using near-infrared imaging. Bit of a mouthful, but you'll get to see what it is all about in just a few moments. So just a bit of an overview. I'm going to explain to you why spatial distribution information is important when it comes to tablet analysis, the spectroscopic techniques that we use to do the analysis, what data we get from that, and then how we use that data to then come to conclusions regarding what actually is important to the manufacturer of these tablets. And then we'll end on a bit of a summary just to give you an overview of everything we've gone through. So just to start off things, so spatial distribution, if you don't know what it is, I've gone to this reliable source of Wikipedia to give me a definition. So we've got a spatial distribution is the arrangement of a phenomenon across the Earth's surface, and a graphical display of such an arrangement an important tool in geographical and environmental statistics. A graphical display of a spatial distribution may summarize raw data directly or may reflect the outcome of more sophisticated data analysis. Many different aspects of a phenomenon can be shown in a single graphical display by using a suitable choice of different colours to represent the differences. Again, a bit of a mouthful, but the main things to point out are the Earth's surface in this talk will be regarding the tablet surface. Graphical display will be, we are going to be using infrared microscopy, so the graphical display will be the visible image we gain from that. Environmental statistics will be the imaging data, so the near-infrared imaging data that we gain from the microscope. And then data analysis will be do the post-processing of the data afterwards to then gain all the conclusions regarding what we're looking at. I'm going to be coming to you with two different types of scenarios or two different stories in terms of why spatial distribution is important when it comes to formulation manufacturers. The first one is going to be a QA/QC environment. So in QA/QC, you want to ensure that the product you're making is performing as it is intended, but also making sure that it is exactly doing the job. So first things first, uniformity. So active pharmaceutical ingredients, so API for short, just to keep my time down. So APIs will be distributed within the tablet. Now, for a QA/QC environment, you need to ensure that the API is well distributed within the tablet. This is for a number of reasons. Firstly, if you don't have equal distribution from your tablet, it might mean that you have issues in your manufacturing process in terms of the mixing of the different ingredients. The other issue might be is it's a common practice today to break tablets in half to split dosage or whatever the pharmacist recommends. So if you have a tablet that has all the API on one half and not the other, when you take the tablet, you actually get an overdose on the one side and not on the other. So uniformity is a big issue that we need to make sure we're addressing. The other one is the concentration of the active files API. So when you're being prescribed different drugs, you need to make sure that the dosage that you're being given and you've been told to take is actually as it should do. And the last one as well is size distribution. So size distribution of the tablet. Again, it allows you to be able to identify any issues when it comes to your manufacturing processes. The other side of the coin in terms of the analysis that we're doing is for counterfeit analysis. So people who manufacture tablets are interested in knowing what else is out there and who are saying that they are producing tablets similar to their own, but actually they're using different materials to do so. So the main one is that to make sure that if someone is selling a drug that says that they have said API involved, firstly, you need to make sure that it's the correct one that they're saying, but also you need to ensure that people are delivering on an API that will deliver an effective treatment. There's quite a few APIs for antimalarial drugs. The 4 or 5 of those are a lot cheaper but less effective when it comes to actually the treatment. So people who are doing counterfeit drugs will use cheaper alternatives to save money, but actually not getting the same treatment as you would from an actual proper API. Again, the concentration of the API within the tablet, you need to make sure that what it says on the box you're getting is actually being delivered. And then the last one is the identification of the excipient. So for people who don't know, excipients is basically the bulk material of the of the tablet. So for instance, a lot of manufacturers use things like lactose to actually build the tablet around. And manufacturers use the excipients, the identification, to actually be able to link a tablet to their own and be able to distinguish between their own and someone else's. So we've got two different sides of the coin, so QA, QC, and then also a bit more of an investigative tool as well. So what is normally used when it comes to tablet analysis is the classic techniques of chromatography. So we've got gas, we've got liquid, and then the mass spec versions of these. And then we have the other products that are the more spectroscopy. We have UV visible spectroscopy. Now, for example, paracetamol, there is an assay test for using UV vis to confirm the presence of paracetamol. FTIR, so this is actually mid-infrared. Again, this is used in pharmaceutical companies quite a lot for QC. So QC of raw materials, but also the product release as well. And then lastly, we have a near-infrared bench spectrometer. So the talk is regarding a near-infrared microscope and near-infrared imaging, but there is also a bench spectrometer that is used for QC again. And what we do is, this might give you a rapid screening technique, and then when it comes to get a false result, you can then take it to the microscope to then do more some troubleshooting. So the instrument that we used for this, so this is Perkin Elmer's Spotlight 400 system. So this is actually, we did the work on the Spotlight 400N. It basically just means near infrared rather than mid. Our microscope system is an integrated system, so you can see that we have the microscope attached to the bench spectrometer. But what the basic message is that we have, you can use near or mid-infrared imaging for doing this analysis, but there are advantages for using near-infrared. Now, when it comes to sampling modes for near-infrared, we have two options. There is transmission, so going through your sample, and then reflectance. So transmission is the best technique for this, but the issue is that you are limited in the sample size, so you're around 1 centimeter in sample size. So when there's something bigger than this, which some tablets are, so we've got to about 5 or 6 centimeters if we change to reflectance. And then we have multiple measurement modes in how we go about that analysis. So point mode is really good. It's just what we say is like the point and shoot. It's really good for being able to identify small areas within a material and identify what those areas are. We can also do mapping, which is, again, good for gaining information over an area. But when it comes a large area like a whole tablet, the mapping uses our single element detector, so it actually becomes too slow. So that's where we move to our linear array, which is unique to Perkin Elmer, and we do our imaging data, and then which is really good for large areas. So there we go. So in terms of the workflow, so we would collect our visible image survey of the tablet, so you can see here, a nice white circle. We then collect the image data, which produces what we call an average near-infrared absorbance map, and then we process the image of that data to actually get to the conclusions. So just before I get into the analysis, some advantages of near-infrared imaging. It's faster than mid-infrared. Now this is due to using, with near-infrared you can use a lower resolution for the measurement. It's a bit confusing in terms of infrared if you have used it. Lower resolution actually means a higher wave number in terms of resolution. If you compare near-infrared imaging versus chromatography, it's non-destructive. So we don't, once we put the sample on the microscope, we don't have to touch it, and you don't have to put it into any solution or anything for that if you're doing the analysis by chromatography. We can do, near-infrared is really good for reflectance measurements, and then, as I mentioned, it's a non-contact measurement. So our two scenarios and our two samples. So we have the first one, which is an uncoated soluble tablet, 17 millimeters in diameter. And then the second one is a coated oval-shaped tablet. These are just the instrument parameters that we use. So you can see we had 16 wavelength resolution, so it is quite high. And we only needed 1 scan per pixel to actually generate this data, which is really good. We can go smaller in terms of pixel size. We use 25 microns. You can go smaller down to 2 or 3 microns. But in general, for tablet analysis, the APIs, they're in the size in the tablet, you don't need to go that small. And then, so we have these two samples, and our data analysis then, basically from what we gain, is we're going to have two scenarios. So the scenario where you have your known ingredients, so you know what API you are using, so then you will most likely have reference spectra for this. And then the other one is having no prior knowledge of your sample at all. So we have two scenarios that I'm going to go through. So sample one is the uncoated tablet. So you can see here we've got a nice white tablet of the visible image. As I mentioned, this is just an average near-infrared absorbance image that we gain from the imaging data. Now, this doesn't really show you much information other than the fact that lots of different pretty colors. So basically what it means is the higher, the brighter the color, so in the whites, pinks and reds, is a higher absorbance, not necessarily any help in you distinguishing different APIs. So that is where we then need to change to our data processing techniques. So the first one we're going to use, as I mentioned, is when you know what you're using. So this is using what we call a correlation map. So basically every pixel within the image you get is a spectrum. So once you have that spectrum, you can compare your pixel from your image and the spectrum there to a reference spectrum. Now, if you do this, you generate what we call a correlation map. So instead of this scale changes, so instead of being absorbance, the brighter the color is actually how correlated the spectrum in that pixel is compared to the reference spectrum you put in. So these are the three APIs that were in this tablet and then the excipient. So you can see at the top we have our four spectra. So we have spectra for references that we can use to generate our correlation maps, which are the four images at the bottom. So we've got acetylsalicylic acid, paracetamol, caffeine and lactose. Now if you're really good at puzzles, you could fit all that together and then create one nice colourful circle. But you can see from a QA/QC part, the acetylsalicylic acid and paracetamol, they're well distributed within the tablet, so we know that we're doing well there. The lactose is the excipient, so you expect that to be everywhere as it's the bulk material. Now, on the box of this sample, it actually said that caffeine was present 8%. There's no caffeine being shown. So 8% is a level on which we can will see it by near-infrared imaging. So whether this was an issue in terms of their mixing, or if it's actually just counterfeit and they claim there's caffeine in there when there's not, I'm not too sure. But you can see how you can use correlation maps to see the distribution of your APIs. The second sample was a nice oval-shaped tablet which is coated, and the coating is usually used to help with digestion or swallowing, so we don't really need to know much in terms of information of that. So what we did is we took cross-sections, and because we were taking cross-sections, it's good to do multiple levels of cross-sections so you get a representation of what you actually, of the whole tablet when you do the analysis. So back into it again, so here is our sectioned tablet with the visible image, and then our near-infrared absorbance image on the right-hand side. So again, we're not getting much information other than we can see the high areas of absorbance. But if we apply the same technique as we did with the last sample and generate correlation maps, we can see how the acetylsalicylic acid, paracetamol and caffeine are distributed within the tablet. So we have two sets of correlation maps here. The first one is what we call an unthresholded correlation map. So basically it means you can see that if you can see this number down here, it's really low correlations and really high. So you can see a lot of bright colors, but you'll see a lot of dark colors where actually the API is not really correlated at all. So you can kind of get an idea of how the APIs are distributed, but you can't see very clearly. So what we do is we set a threshold of the correlation number, and then we generate something that looks like this. So now you can see a lot easier where your APIs are distributed within your tablet by creating a threshold of the correlation value. And again, if you were really good at puzzles and you could put those three images together, then you would be able to see how it all molds into one tablet. So that is the reference spectra. So that's using if you know the materials and you know your APIs that are involved. The other option is when you don't know anything about your sample. So this is what we call, within our software it's called the show structure function. It's just a single click command. But what we're essentially doing, we're applying principal component analysis to the imaging data to generate some information from that. If you don't know principal component analysis, a bit of a mouthful, it's chemometrics basically, it's statistics that then let us be able to gain information from our data. So as I said, you don't need any prior knowledge of your sample when you use chemometrics. The software will do everything for you. As you can see, we've got 3 different colors here, so it's identified 3 main areas in terms of what we're actually seeing in chemistry. So different colors mean different chemistry. So we have green, dark blue, and then a lighter blue on the outside too. So if we now compare the principal component analysis versus correlation map, so this is the same absorbance image here compared. So the PCA, you can see we have the green matches the first one. The lighter blue matches this one. And then the darker blue matches this one. So no matter if you have the reference material or not, there are ways to be able to get the same information on both methods, and they give you the exact same information both times. So for near-infrared imaging to combat forms of drug counterfeiting, it's really good for being able to make sure, first of all, if there is API present, or to see if there is the correct or incorrect API present in the tablet. We can also use the data to make sure that the concentration of the API is as it should be, and then also illegitimate excipients that have been used by other manufacturers. Only limitation is currently at the moment we are not able to use near-infrared imaging to look into falsified expiry dates. So just in a summary, so the near-infrared data that we get from imaging of tablets generates really useful spatial distribution information. And with this information, whether it be for a QA/QC environment or troubleshooting with counterfeiting, we can use a range of algorithms to make sure that your distribution is as it should be, but then also be able to use quantitative estimates on the ingredients as well as possible. And whilst this is a talk around mostly, all tablet analysis in pharmaceuticals, the same techniques can be applied to other industries or other samples. So for example, foods, polymers, or contaminants. And that is all I have. So thank you very much. Any questions? Yeah.
Thank you for the presentation. So you're seeing a 2-dimensional spatial image. What is the penetration of the infrared, and how much do you know about the 3-dimensional?
How much do you know about what, sorry?
The 3rd dimension.
The 3rd dimension.
Through the volume.
Yeah, so it depends on how you do the analysis. So as I mentioned, for transmission, it will go right through the sample if you have about a centimetre in terms of the thickness of the sample. Whereas reflectance, so are you familiar with diffuse reflectance? Yeah. So you'll get a few microns, again, it will depend on your sample, but you'll get a few microns penetration in your sample because the beam will come down, it will penetrate through, and it bounces around through the molecules to then come back up. So you obviously, depending on your sample, you will get more information sometimes by going deeper. Yeah.
And how do you separate out the specular reflection from the surface? Are there algorithms?
Sorry.
How do you separate out the specular reflections from the surface of the tablet?
It's the specular reflectance. We don't need. So you don't need to worry about that. I would say because you're getting the information. The information you need is the ones that come back to the detector. So a nice flat surface, and it works really well.
Okay. What if the surface was, let's say, a glass fibre filter?
Yeah.
Rather than a solid tablet.
Glass fibre filters you can usually do by transmission, but if you're doing mid-infrared, glass loves mid-infrared, so it'll just absorb it. So it's not the best. The infrared would be better, but yeah. So
okay.
It is ways around it.
Okay, thank you.
Any other questions? No? Then I think we're done, and you can go and look around the stands, grab some freebies, steal all the chocolates.